to Calculus 3 video lecture number 6 on cylinders and quadric surfaces. So in this video, we're going to go over how to graph cylinders and primarily quadric surfaces. And just to reiterate, when we talk about cylinders in space, a cylinder is a surface that consists of all of the lines, which are called rulings, that are parallel to a given line and pass through a given plane curve. What does that mean? Basically, when you see an equation and there's only two variables instead of three, what you do is you're dealing with a cylinder. It doesn't look like the typical cylindrical can necessarily that you're thinking of, a circular cylinder. All it means is you're going to draw the graph in the plane consisting of the two variables that you see, and then you're going to project that graph along the axis of the variable that's missing. Okay, so let's look at an example here. The first one actually is a circular cylinder in free space. So graph x squared plus y squared equals 4. Notice z is missing, so I'm going to project the graph of x squared plus y squared equals 4 in the xy plane along the z-axis. So let's begin. We'll set up our coordinate system. I know in the xy plane, x squared plus y squared equals 4 is going to be a circle. And then if I project that along the z-axis, then I will get a circular cylinder. So x-axis, y-axis, z-axis. And I can tell this is a circle with radius 2. So I'll go ahead and scale off my axes. Okay, so you're going to draw the trace in the xy plane of the circle with radius 2. And then I'm going to project that along the z-axis. And there's a couple ways that you can do it, but I've talked about before, you could just pick some sort of arbitrary distance and then add that onto each of your points. I'm freestyling today. That one's not perfect. Okay, one more. And then you have your projection, okay? And we know that it goes infinitely up and down, but this just gives us an idea, kind of. You can shade the part that's towards you. Okay, what about the following? Graph y equals z squared. So x is missing. I'm going to graph y equals z squared. That's going to be a parabola opening up along the y-axis, and then I'm going to project that graph, that parabola, along the x-axis, okay? So here we go. Here's the z-axis. Here's the x-axis. Y-axis. So first I'm just going to draw the parabola in the YZ plane. Okay, so we'll scale a little bit. 2, 3, 4, that should be good. 1, 2, 1, 2. Okay, so if I draw the parabola in the YZ plane, it's going to go through 0, 0, well, 0, 0, 0, right? This is for all x is 0. Opening up here and here. Okay, and then from there, I want to project this parallel to the x-axis. So what I'm going to do, pick a distance and draw a line segment parallel to the x-axis and just add it on several times throughout. Okay, and then we're going to connect those. And that extends forever, but this gives us an idea kind of what it's looking like. So it looks like an infinite piece of paper that's folded somewhat. You can add some shading to help with the perspective. Okay. Good. Let's look at one more. We're going to graph y equals cosine of x. So in this case, z is missing. So I'm going to draw the graph in the xy plane and then project it in the direction of the z-axis. Let me do it in two pieces. So here's positive y-axis, negative y-axis. I'm only going to need to go to positive 1 and negative 1, right? Since we're graphing cosine. And then here's my z-axis, here's the x-axis, and I'll just graph it maybe for one period. So that'll be pi over 2, pi, 3 pi over 2, there's 2 pi. Okay, so if we're graphing cosine, at 0, cosine's 1, at pi over 2, cosine's 0, at pi, cosine's -1, back to 0, and then it ends at 1. So here's the graph of cosine in the xy plane. Now I need to project this in the z direction. Okay, this one I am gonna take special effort to make sure it looks perfect. There's one. Get your ruler out if you need to. And here's our graph. Beautiful. And then if you want to shade a little bit to show which side's towards you, right? This is the side that's closest to, this is the exterior of this cylindrical surface. So this is still called a cylinder, okay? Good. Now let's move on to the heart of the lesson. And we're going to consider quadric surfaces. Now these are more challenging to graph. The general form of a quadric surface is that you have ax squared plus by squared plus cz squared, and then you can have these mixed terms which make life a little bit of a nightmare. But generally we'll work with the much simpler version where we just have ax squared plus by squared plus cz squared plus just a constant is 0. So we're not going to rotate them, or maybe you'll have like a linear z term mixed in there. Okay. Now, quadric surfaces are essentially three-dimensional analogs of conic sections. So if you need a review of conic sections, I have a video linked right here, and you can review them in 2-space. And these quadric surfaces are very closely related to conics. Their traces in the coordinate planes will often be conic sections. And we've previously used traces to help us sketch simple graphs like 2x plus 4y plus 3z equals 6. Remember, that was the graph of a plane. And the xy trace is the intersection of that graph with the xy plane, meaning those points for which z is equal to 0. So if you'll check the previous lesson, when we graphed that plane, we graphed all three traces, and then we put it together to come up with what the graph of the plane was looking like. Now, traces can be helpful in identifying and sketching graphs, but it's typically best to first identify what kind of surface you're graphing so you know what your end goal is going to be, and determine what its orientation is instead of just sketching the traces and then haphazardly trying to assemble them into a graph. So there's 6 quadric surfaces that we're going to consider. Some of them are going to be more relevant throughout the course than others, and I'll point those out to you. First one is the ellipsoid. And it has the form x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. And the name tells you that all the traces are ellipses. And you can see clearly it looks like the three-dimensional version of an ellipse. So we're going to sketch the graph of the following ellipsoid. I know it's an ellipsoid because all 3 variables, x, y, and z, are squared and they're all positive. Okay, so first thing I want to do is put it in standard form in order to graph an ellipsoid. So I'm going to divide through, that way this constant here is a 1. So I'll have x squared over 4 plus y squared, I'll just put it over 1 so we know, plus z squared over 4 is equal to 1. Okay, and then now we're going to figure out what all the traces are. So let's set up our coordinate axes here. So there's my z-axis, x-axis, y-axis. And it looks like if I just scale up to 2, that should be perfect. Okay, so let's get all the traces. So first, if x is equal to 0, that would be the trace in the YZ plane. I would have the following equation left. I'd have y squared over 1 plus z squared over 4 is equal to 1. Well, this is the graph of an ellipse in the YZ plane. So in the YZ plane, in the Y direction, I'm going to move 1 unit, in the Z direction 2. So I have that trace right there. Okay, that part's pretty straightforward. Now let's consider another trace. So let's do if Y is 0, that would be the trace in the XZ plane. So if Y is 0, we're going to have x squared over 4 plus z squared over 4 equals 1. Technically, that's a circle, right? Since both a and b are equal. Okay, so in the xz plane, I'm going to have a circle, radius 2. Okay, and then lastly, let's look at the trace in the xz plane. So if z is equal to 0, then that's the trace in the xy plane. Sorry if I said xz earlier. In the xy plane. And so then you'd have x squared over 4 plus y squared over 1 equals 1. This is in the xy plane. And these are actually pretty easy to draw because you already have all these points, right? So in the xy plane, I'll have 2, 0, this point here, this one back here, this one down here. Okay, so there's our ellipsoid. Looks pretty good if you ask me. You can add some shading if you want. Up to you, lightly though, okay? Don't make your graph a cluttered mess afterwards. Okay, the ellipsoid comes up relatively often. Now let's look at another quadric surface, and that is the hyperboloid of one sheet. Okay, what to notice? So first of all 3 variables are squared. You have x squared, y squared, z squared equals 1. One of the terms is negative, okay? It doesn't necessarily have to be z that's negative. We call it a hyperboloid of one sheet because there's only one negative variable in the equation. So one negative variable means there's one sheet. Notice here in the example, we have the graph of the hyperboloid of one sheet and it's opening or oriented along the z-axis. And so the hyperboloid will always be oriented along the axis of the negative term. Okay, so in this case, let's see how we would sketch the graph of the following. We have x squared over 9 minus y squared plus z squared equals 1. So I know it's a hyperboloid of one sheet because y squared is the only negative term. All 3 variables are squared. It's equal to 1. So this is going to be a hyperboloid of one sheet oriented or opening along, in this case, the y-axis, since that's the negative variable. Okay, so we're going to get our traces. And let me set up my axes here. Z, X, always label them. And then here's the y-axis. Okay. Now let's get our traces. Okay. So if x is equal to 0, I would have the equation negative y squared plus z squared equals 1. Well, it looks more normal if I write z squared minus y squared equals 1. That's a hyperbola in the xz plane. If y is equal to 0, then I would have x squared over 9 plus z squared is equal to 1. That's an ellipse in the xz plane. And then lastly, if z is equal to 0, then you're going to have x squared over 9 minus y squared equals 1. That's another hyperbola in the xy plane. Okay, word of advice when you're graphing these traces for it to not fall apart at the seams. What you want to do is actually graph the ellipse, the trace that's an ellipse first, okay? That'll help orient you a little bit better. So I have an ellipse. In the x direction, I'm going to move 3 units from the center. And then in the z direction, I'm going to move up and down 1 unit. So I have this ellipse in the xz plane. Okay? Now I'm going to draw the other traces. So if x is equal to 0, well, let's draw the other hyperbola first, actually. That one will be more fun. So I'm going to draw the hyperbola in the xy plane, x squared over 9 minus y squared is equal to 1. So since x is the positive variable, it's going to open along the x-axis, and it's in the xy plane. So part of it is going to be coming at us this way, and then the other part's going to be going away from us that way. Okay. And then lastly, I'm going to draw this trace here, z squared minus y squared equals 1. So that's a hyperbola. That one's going to be opening along the z-axis, and it's going to be in the yz plane. So I'll do it here. It's kind of straight on. This is the very top part. Maybe I should. For perspective purposes, it's a little tricky. And then this one is at the very, very bottom. So this is, you can't really see that part maybe. Okay. Now you can kind of start adding more traces if you like you can let y vary and you're going to get more ellipses. What do I mean by that? So if you let y vary, then you're going to get another ellipse here, another one here, so on and so forth. Okay, and this one's pretty rough to draw, so don't sweat it. Something like this. So you can see it's opening along the y-axis. Good news, it doesn't come up too often, but just as long as you get the idea of the traces. And I know we're not all art majors, so as long as the math is there and the traces are there and everything's labeled nicely, that's good enough for our purposes. Okay. Hyperboloid of 2 sheets. So what to notice about this equation? Again, all 3 variables are squared. In this case, 2 of them are negative, okay? And same thing as before, 2 negatives implies that there's going to be 2 sheets. In this case, the hyperboloid will be oriented along or opening up along the axis of the non-negative term. So for a hyperboloid of 1 sheet, it was opening up along the axis of the negative term. In this case, it's the non-negative one. It's just going to always open up along the axis of the oddball, right? Whoever's outnumbered. And notice here, this one's opening up along the x-axis, and that's because x squared was the positive one. Okay, so now let's look at an example. How to sketch this one isn't so tricky. So sketch the graph of negative x squared plus y squared over 9 minus z squared over 9 equals 1. So right away I can tell, all right, this one's going to be oriented or opening up along the y-axis. How do I know that? Because that's the only positive term. Okay, so let's get all of our traces here. So if x is equal to 0, I'm going to have y squared over 9 minus z squared over 9 equals 1. So that's a hyperbola. If y is equal to 0, I'm going to have negative x squared minus z squared over 9 equals 1. Now think for a second. Is it possible, like if I were to get rid of the negatives, I could just multiply everything through, right? So I'd have x squared plus z squared over 9 equals negative 1. Is it possible for it to equal a negative number if you're summing up the square of 2 terms? No, that's not possible. So what do we say? This trace won't yield a graph. This is a degenerate case. You might remember that from studying conics. And then the last trace we're going to consider is if z is equal to 0. And so when we would have, let's see, negative x squared plus y squared over 9 equals 1. So that's another hyperbola. Now, sometimes when you get a degenerate case, you need more traces still. So then what you would do is let y equal something other than 0 to help you graph. But in this case, these two traces are going to be plenty because I know it's oriented along the y-axis and I can draw enough of a graph with what I have. So here we go. There's my z-axis, x-axis. Here's the y. And I'm basically just going to draw two sets of hyperbolas, right? 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, so let's see. In the YZ plane, I have a hyperbola that's going to open in the y direction, right? Since y is positive. And the vertices are going to be at plus or minus 3. And this is in the YZ plane. So just straight on. Something like this. And something like this. Okay, so that one's done. Then I have a degenerate case for y equals 0. And then I have another hyperbola in the xy plane. Now this one's going to open again in the y direction because that's the positive term. So in the xy plane, x is only going to be, well, you won't see it because that's the negative one. So I'm just going to worry about where y is. And this one's basically coming at us, right? So it's this way, a little more flat. That's in the xy plane. Like that. Okay, and then if you want to kind of add a few little dashed lines to connect them and show that you have the graph and they look like almost, we haven't done paraboloids yet, but it looks like two paraboloids somewhat. And you can add some shading if you want. Okay, so even with just two traces, this one's very manageable. Nice. Okay, next example, we have the cone. So what to notice about the cone? Okay, all three variables are squared. You have x squared, y squared, and z squared. However, it doesn't equal 1, it equals 0. Also, one of the variables is negative, only one. So sometimes we'll rearrange the equation and solve for that opposite term variable. So you'd have z squared over c squared equals x squared over a squared plus y squared over b squared. Okay? Now, the cone will be oriented along, surprise, surprise, the negative or isolated variable. Okay, and it's very common. Notice if everything's equal to 1, say a, b, and c are 1, sometimes we'll rewrite this. If you just see z equals the square root of x squared plus y squared, that's a half cone. This will come up so much throughout the rest of the course, that half cone. Okay, so, I mean, this cone is probably different than the typical way you think of a cone. You might think of just the half cone when you hear the word cone, but really there's two portions to the graph. All right, let's sketch the graph of x squared equals y squared over 16 plus z squared over 4. So I know it's a cone oriented along the x-axis. Okay, so let's get some of the traces. So if x is equal to 0, then I'm going to have y squared over 16 plus z squared over 4 equals 0. Multiplying everything through by 16, I'm going to get y squared plus 4z squared equals 0. This is going to be degenerate. The only solution is 0, 0, 0. So no good comes from that trace. Okay, what if y is equal to 0? So if y is equal to 0, then I get x squared equals z squared over 4. Then I end up with 4x squared equals z squared. So z equals plus or minus 2x. So these are two lines, okay? And then lastly, if z is equal to 0, then I get x squared equals y squared over 16. So 4x squared is equal, or excuse me, I already took the square root in my head. 16x squared is equal to y squared. So you get y equals plus or minus 4x. So those are two lines as well. So how do you get the rest of the cone? You're going to have to let x equal something other than 0. And if x equals something other than 0, you're going to get a series of ellipses. Think about it. So for example, if x is 1, you're going to get an ellipse, right, in the YZ plane, but where x is equal to 1. So this can be a little bit tricky to have all the parts come together, especially with constants like 16 and 4. But the good news is most of the cones that we're going to graph the remainder of the semester are pretty generic. It's just going to be cones like this. So you don't have to go through too much painstaking detail to get a workable graph, okay? The most important thing is that you can see the equation and recognize that it's a cone. That's the crucial part. So anyways, let's try our best, see what happens. X, Y, Z. So y equals plus or minus 4x. So that's a slope of 4. 1, 2, 3, 4. 1, 2, 3, 4. So it's going to go through this point, 0, 0 in the xy plane. And then again, there's the slope of negative 4. And we have z equals plus or minus 2x. So if I go up 2 in the z direction, I'm going to go over 1 in the y direction, in the x direction. So that would be here to the origin. Ooh, no. I've got this line, and then one more over here. Okay. So what you can do is make some more traces if you want to let x equal 1, for example. If x is 1, then you would get y squared over 16 plus z squared over 4 equals 1. So that's going to be an ellipse in the YZ plane, right? But where x is equal to 1. And so in the y direction, you would move 4 units. In the z direction, you would move up and down 2 units. So you would get this ellipse, but then that would have to be where x is equal to 1. So I would shift it over a little bit here. Let's copy it, and then I need another one because if x is negative 1, I'd get the same thing. So maybe somewhere over there. And you can keep adding them together. Now it's looking really messy, but the main idea is the cone will open up along the x-axis. So it'll work out nicely if you don't have constants like 16 in the equation. But basically you're going to have a line here, a line here, and then you're going to have this series of ellipses that make your cone. Okay, that's the main idea. So put that graph together how you need to, but recognizing the form is the most important part. Okay, moving on, the elliptic paraboloid. This one's pretty easy to graph. So you have one variable that's not squared, the other two are squared, and they have the same sign. So notice that one variable is not squared, the other two have the same sign. And the paraboloid will be oriented along, well, which one's the oddball? The unsquared variable. Now these elliptic paraboloids we will graph frequently the remainder of the course. So sketch the graph of x equals y squared plus z squared. So I can tell right now this one's going to be opening along the x-axis. So if x is equal to 0, I'm going to get 0 equals y squared plus z squared. That's degenerate. That's just a single point, 0, 0. Not interesting. Okay, if y is equal to 0, I get x equals z squared. That's a parabola in the xz plane. And if z is equal to 0, then I get x equals y squared. That's another parabola, this time in the xy plane. Okay, so let's graph this one. Z-axis, x-axis, y-axis. All right, so if y is 0, I have a parabola in the xz plane. Since it's x equals z squared, it's going to be opening up in the x direction. So it's basically coming at us this way. That's underneath. And then if z is 0, I have x equals y squared. So this is, again, a parabola opening up in the x direction in the xy plane. So this one's coming this way. This one's beneath it. Okay, so the purple one is x equals y squared. And then the light blue one is x equals z squared. And then if you want to connect them or do something to add some perspective, go ahead. Okay. The most important thing is to determine which axis it's oriented or opening up along. Okay, good. That one will come up very frequently. And last but not least, the hyperbolic paraboloid. Now, how to notice that you're dealing with the graph of a hyperbolic paraboloid. So one of the variables is not squared, the other two are both squared, and one of them is negative. Now this is also known or referred to as the saddle. And that's important to remember later on when we study maxima and minima in the course. And so it looks kind of like a Pringle chip. It's oriented with the head along the oddball, which would be the non-squared term. And it's facing the squared term that is positive. Okay, so we're going to sketch the graph of the hyperbolic paraboloid z equals y squared minus x squared. So basically the same one that's in the example up above, but we're going to do it. And this one has the head on the positive z facing the y-axis. Okay, here we go. So first things first, let's get our traces. So if I let x equals 0, then I get z is equal to y squared. So that's a parabola. Then if I let y equals 0, I get z equals negative x squared. That's another parabola. Here's where you have to be careful. If I let z equal 0, all I get is x squared equals y squared, which means y equals plus or minus x. That's two lines, but that's not going to really help me graph the hyperbolic paraboloid. What I need to do is allow for traces where z equals something other than 0. So let's start off by sketching what we have so far, and then I'll add in additional traces so you can see what's going on. So here's my z-axis, and then here's the x-axis and the y-axis. And I'll start off by sketching the two parabolas that we have, okay? So x-axis, y-axis, z-axis. And let's see, I'll do some scaling just to make sure it's precise. 1, 2, 1, 2, 1, 2, 2, 3, 4. 1, 2, 3, 4. Okay, and then let's go here to -2. All right, so z equals y squared. That parabola is going to be here, 0, 0, 1, 1, -1, 1, 2, 4, -2, 4. I'm not loving where this point is, and it will be a problem later on, so we have to fix it. Okay, much better. So we've got this parabola here. Okay, good. Then I have, so this one's done. It's this guy. Okay, then I have z equals -x squared. Okay, so that's going to be in the xz plane. So this one's coming towards us this way. And then I'll do it dash so you see like that part's going away from us. Okay, and then the lines y equals plus or minus x, I'm not going to draw them. It really just makes your graph a mess. Just know that it's not going to be helpful and you're going to have to let z equal something other than 0 right now. Okay, so let's see how to proceed. Say I were to let z equal 1. So if z is 1, then I get 1 equals y squared minus x squared. That's a hyperbola opening in y. And as long as I have y squared minus x squared equals some constant k, right, where k is greater than 0, I get just a series of hyperbolas that are parallel to the xy plane. So I'm just going to draw a series of them right now. Okay, so these are hyperbolas that are parallel to the xy plane, but they're going to be moving up and down. They're just going to be moving up in the positive z direction, okay? So you would have, let me do a different color. So you would have maybe hyperbola this way, and then it's coming this way. And then another one, we're moving up in the z direction. I'm letting z equal k, k is a constant, etc. Okay, very nice. Now, what if k is negative? So say I let z equal -1. So if y squared minus x squared equals k, which is negative, like y squared minus x squared equals -1, then I'd get x squared minus y squared equals +1. So that's a hyperbola opening in x. So now as I move down the z-axis, I get hyperbolas that are coming towards us in the x direction and away from us in the negative x direction. And that's going to be difficult to draw. So I'm just going to do one. So you can imagine it'll be kind of coming towards us this way. And then on the back side, there's going to be another one. All right. And sometimes less is more with these. If you have too many traces, it turns into too much of a mess on your paper. So then now how to connect all of this, right? So you want this front portion to be longer. I'm going to connect it here. These keep going in the back. Okay, and then they're going to eventually hit that parabola, the hyperbola that I didn't draw that was going away from us, right, in the negative x direction. And then same thing over here. So this front portion, you can connect it. And then that back portion, these should all connect too. Okay, good. That one's brutal. Won't come up too often. The main thing to remember is that this saddle point, because we're going to study it later, depending on how you're looking, it can be both the minimum and maximum point of the graph, right? Depending on where you're looking. All right. Now we're going to find it necessary later in the semester to sketch regions that are bounded by 2 or more surfaces. So let's practice a little bit. These are going to be rough sketches for this first one. So sketch the region bounded by z equals rad x squared plus y squared and z equals 2 minus x squared minus y squared. So identifying them is really the most important part. This first graph is going to be a half cone. And then if you'll remember, z equals x squared plus y squared, that's your elliptic paraboloid. Well, what does it mean if you have 2 minus x squared minus y squared? Well, that's an elliptic paraboloid that's opening down, and it's been shifted up 2 units, so the vertex is at 0, 0, 2. Okay? If it's necessary to find exactly where they intersect, you can do so, but right now we just want to get an idea how you would graph 2 surfaces simultaneously. Okay? So here's y-axis, z-axis, x-axis. So we've got the half cone. Most of the time, this is going to be good enough of a cone. You don't have to go through all the traces. And then we've got the elliptic paraboloid, whose vertex is up there, and it's opening downward. Okay. So what's the region bounded by these 2 curves? It's going to be this portion here. If you were to zoom in and maybe do like a separate 3D sketch, it would look sort of like a snow cone, right? There's that portion from the elliptic paraboloid, and then that portion below from the cone. That's the region that's bounded. Okay, and then last example, sketch the region in the first octant only, that's bounded by the coordinate planes, z equals 4 minus x squared, and x plus y equals 4. Okay. So here we go. So we're only in the first octant. So I'm just going to do positive z-axis, positive x-axis, positive y-axis. And we're bounded by the coordinate planes. Okay, that forces us to be in the first octant. I have z equals 4 minus x squared. So that's a parabola that's opening downward in the xz plane. That's 4. It's going to hit the x-axis here at 2. So I've got this portion here. Okay. And notice that y is missing. So this gets projected parallel to the y-axis. Okay. Something like this is going on. So that's z equals 4 minus x squared, and then x plus y equals 4, that's a plane, right? And the intercepts, I can draw them right now. 1, 2, 3, 4. 3, 4. Okay, so here's this plane, and I'm only interested in the portion in the first octant. So I'm going to project it parallel to the z-axis. All right, and then now I want to sketch the region that is bounded by all of these. Well, imagine here, this plane is cutting through z equals 4 minus x squared. You can imagine the intersection. It's going to come through and slice it right here. And you're going to have this portion just flat here, cut by the plane, right, at an angle. And then I also have the front side across this way. Okay, so if you wanted to do just a separate sketch of what remains, we can do that, so it's cleaned up. So I know it's going to cut through here where x is 2, and it's going to go up until where y is 4, right? And z is up here at 4. And so I'll have this point down to x equals 2, and then from y equals 4, that's fine, that's going to still be there. This will still be there. Then this is going to get cut, right? So it's going to intersect when x is 2 and y is 2. 2 plus 2 is 4. Yay. So that'll be right there at that angle. That's the plane cutting through. And then we have this portion here. If you want to add a little perspective, Do it nicely though. There we go. So it doesn't exactly match that first picture. I scaled it differently, but that's the same idea. That's just what remains. So here's that blue side. And then that other face that was cut by the plane. Okay, this is more of a sneak preview of what's to come. Focus on getting those quadric surfaces under control in the meantime, and this is what you have to look forward to.